going. So I'm going to introduce Hugo to you. So Hugo, I don't know if everyone's aware, so his new position is he's the leader of a brand new Google Brain group in Montreal. So that's a position he's starting sometime in the next several months. But I got to know Hugo. He was a postdoc here, and just found out it was longer than I realized. He was a postdoc here 7 years ago, and was here for a couple of years. Before that, he got his PhD in Montreal with Joshua Bengio, and then went on to, after postdocing here, we went to a startup, a wet lab, and then we got acquired by Twitter, and has been in Twitter since then. Also, he was a faculty member at the University of Sherbrooke. And he's involved in a lot of organizational things, so he's one of the leaders of the new and rapidly growing ICARE conference, the Conference on Learning Representation, which is kind of started off as a deep learning meeting, but is just blossomed into a huge meeting these days. My favorite image, so Hugo's chair, and often the chair of a meeting is very stressed, especially a meeting is like that. But I was very impressed last year. The meeting was in Puerto Rico, and my image, I saw Hugo, instead of running around crazy, I remember him sitting by the pool in his bathing suit with the sunglasses on, so he was very relaxed. It was a good meeting organizer.
Was that at the end or the beginning of their conference? Oh, okay.
Yeah. But Hugo does great work, so he's not, he's one of the star in deep learning, and knows a lot of different areas, so I've collaborated with him, continue to collaborate with him. He's a lot of fun to work with. He knows a lot of background work and is very quick on picking up new ideas and coming up with his own ideas. So he's a great researcher. So very happy to have him here today. So he's going to talk about autoregressive generative models with deep learning.
Thank you, Rich. So yes, thanks for the invitation. I'm really happy to come back. It's been a little while since I came here, so it's really great to be back. And the work that I decided to talk about, I felt it was fitting to talk about autoregressive models for a few reasons. The main one is that I actually started working on this, and I'm not going to touch only on my contributions. I'm going to talk about some very recent work that comes mostly from DeepMind. But the first paper that I published on the topic was actually when I started doing the work when I was here as a postdoc. And in fact, I was very fortunate to be a postdoc here, and I was essentially officially in Jeff's group, though I also interacted with Rich. But I was very fortunate that Jeff had the vision that for postdocs, he would just hire a lot of qualified people and give them the freedom to work on some of their own ideas. And so I owe Jeff a lot for actually coming up with some of these ideas with another great postdoc, Ian Murray, that was there then. So Jeff, thanks for that. And it's also, I feel, so this idea sort of, for me, started in Toronto. And also in the recent years, you've seen some people in the industry, in particular DeepMind, starting to explore these ideas and pushing them further. And so I know there's a component here in these meetings where it's about academics meeting people from industry, and you start seeing some of this happening with these ideas now translating to still pretty research-oriented industrial group, but in industry nevertheless. So some of these ideas might actually, grow into full-blown interesting applications in the coming years. So I'm going to talk about generative models in general, but specifically one approach to generative models, which is autoregressive models. What are generative models? They are models you can train on a data set, and then once you have trained your model, you can generate new observations that, if your model is successful, could have come from the same data set. Looks like samples generated from the same distribution from which you gathered your data. And also, certain generative models, and autoregressive models have this property, will also tell you, if I give you an observation, how likely is it that it might have come from this data set, that it might have been generated from the unknown distribution that generated your data. So why would you want such models? Well, there are certain fairly simple applications. One of them is to apply generative models to images to do things such as denoise images or do super resolution, so take a low resolution, low quality version of an image, and actually generate a high resolution, higher quality version of that image. And intuitively, the idea is that if you've trained your model on high quality images in general, it gives you a prior for what should high resolution, high quality images look like. So then you can solve a problem of, well, for this low resolution version of an image, give me a high resolution version of an image that has high probability under that generative model, but also is fairly likely to come from, to be the high resolution version of this image here. Okay, so that's one application, and this is taken from a recent submission on arXiv from my now ex-colleagues at Twitter that used to be in Magic Pony Technologies. So that's about generating new observations of a single image. Another interesting application is to use generative models to try to make predictions about the future, about what could happen in an environment if you have an agent taking actions, what would be observed if an agent took a series of actions. This is a component that's very important behind the success of AlphaGo, for instance, where the agent will try to simulate what would happen if I made this move. What would be the next, configuration of the board? Now, for the game of Go, it's pretty easy to do this because, you can actually literally write down the rules of Go. So it's easy to implement a simulator and know what would happen if I if I made a given move. But if you're in a real environment, or even in a game environment like an Atari game, it's actually not easy necessarily, or not obvious how you could sort of write down a program that, given a command, say, on your controller, would give you, okay, what is going to happen next? What will you observe next? And recently, people in Michigan, from Unlikely's group in particular, actually show that you can train generative models that, given the previous frames of a game and an action that you want to make, will give you what will be the next frame of that game. And you can imagine that this might be useful for planning how to be successful at this game, because you can do longer-term planning of the series of actions you could do and sort of measure by looking at the state of the game, okay, was that successful or not? And to do something like this, you will need a generative model. And even if you're not interested in generating observations, generative models may be useful for obtaining another learning signal for training a classifier. In particular, because generative models can be trained on unlabeled data, you might be able to exploit that unlabeled data to improve the quality of your classifier that might only have access to a limited amount of labeled data. And the reason for this is that effectively a generative model, say if you were to train it on images of handwritten digits, it's going to try to learn to sample things like this and not things like that. So what it means is that this model somewhere in its internal workings actually must know what makes this a special image that it should be generated and makes it different from random images like this one. And so this means that presumably behind the model there's some informal understanding of what's, in this case, a pen stroke, or what are the different types of digits that are present in my data set. And of course, knowing about this might be useful to, say, categorizing images between the different digits that they represent. And so that's another application for generative models. I should say, at any point, please don't hesitate to interrupt me. I'll be happy to make this more interactive and take questions. So before I go into autoregressive models specifically, I just want to cover a few other approaches for generative modeling. One approach is to use directed graphical models with several, perhaps just one or several hidden layers or latent representations. So in this context, the way we're going to model our data, and I'm going to use X for our notation of observations. So X could be the pixels in an image, say. I'm going to assume that this image X was generated by first sampling from some prior distribution a higher level latent representation that is not observed and that will need to be learned. So within that layer, maybe there's the choice of what kind of digit I'm going to draw. And then from this, you might sample a slightly lower level version or lower level representation of my image X given my high level representation at my top layer. Maybe here, the network is sort of choosing what where exactly would it position the digit in the image, what kind of strokes it would decide to draw. And then you might have another layer that will, again, be sampled perhaps just from the latent representation right on top of it. Here, you might make more specific choices as to the appearance of that character. And then finally, from the lowest level latent representation, you would generate an observation X. And so in this context, the distribution over my observations X, P of X, corresponds to taking this joint distribution over the observations and all the latents and summing over all the possible values of these latent representations, which is usually intractable. And that complicates a little bit how we can train such models. Nevertheless, recently we've seen some very successful algorithms for training versions of directed graphical models like that. You might know about variational autoencoders, or VAEs, which uses a variational approach. Generative adversarial networks are another version where you have usually only stochasticity at the top level, at the highest level of latent representation, and then going through several neural network layers eventually draws, say, an image or some observation. And it uses this interesting minimax kind of approach for training such models. Sparse coding can be understood as a directed graphical model. Helmholtz machines, which were essentially a version of VAE, but essentially with discrete variables in the hidden representations as opposed to continuous. So there's been a lot of work around this particular framework. One of the pros for such models is that it's easy to sample from. It's with ancestral sampling, you just sample the top level latent representation, and then usually you can trivially sample the next bottom representation and moving downwards like that all the way to the input representation. However, computing actually the probability of some observation, which is sometimes important to get if you want to do things like, it's often useful if you want to do things like super resolution, is usually intractable because you have to integrate out all the latent representations. And that, for similar reasons, it makes such models harder to train. Another type of model are undirected graphical models. So in this case, instead of determining a joint distribution over some input and a sequence of layers as just a product of a series of conditionals, which make statements about the conditional independencies between your variables, you will actually just define a joint energy function over the values of all the layers, the input layer and all the hidden layers. And then to get a distribution, you will simply exponentiate it and take the negative energy so that things with low energy have high probability. And then you normalize. So this constant Z requires summing over all values of X, H1, H2, H3 here. Examples of such models are deep Boltzmann machines, the restricted Boltzmann machine being the one hidden layer version of that. Deep energy models is another one. So some of its pros, in particular for a single hidden layer or for certain types of energy-based models, you can actually not compute P of X exactly, but at least get P of X up to a multiplicative scalar, which might be sufficient to doing things like multi-resolution, denoising or upscaling of images. One of the disadvantages, again, they tend to be harder to train because of the constant here that usually we can only approximate. They're also technically harder to sample from because we can't just do a ancestral sampling and get an exact sample. Usually you have to do some form of MCMC in these models. So they're generative models, but I think some people will argue that they're not really because you're never guaranteed that you have an exact sample from your distribution. If you're using MCMC, it's only eventually converging to an equilibrium distribution that matches the real distribution. And so what I'll focus on is instead what I'm writing down here as a separate family, though some could argue it's a form of directed graphical model, but it's different in a key way. I call those autoregressive generative models. The way they work is that you take your observation space X, and then you're going to determine an ordering of the dimensions. To make everything simple, just assume we're going to go from the first dimension to the last one, assuming there's already a sort of given ordering, natural ordering. And then, well, knowing that any joint distribution can be written down as the product of the conditionals over each dimension given the values of the previous dimensions, well, all I'm going to do here is just come up with a model for those conditionals. I'm going to define a parametric, usually, model for what these conditionals are. And I'm going to train my model of all of these conditionals. So I'm going to discuss a few versions of this idea here, such as Nade and Made, which I'll discuss a bit later. And towards the end, I'll talk about pixel CNN, which is kind of, for images, essentially the state of the art, at least when it comes to autoregressive models. You can represent that as a graphical model like this. So notice that here there's no explicit notion of a stochastic latent representation for my observations. I'm directly representing within some parametric form, and specifically we'll use neural nets here, all of these conditionals. So some of its properties is that in this case, P of X is actually tractable. As long as each of these conditionals I can compute exactly and tractably, then getting the joint distribution is just querying my model for each of the conditionals and then taking the product of all of these probabilities. That's pretty easy. So it means it makes it tractable. It's also, because of that, often easy to train by maximum likelihood. If I can compute P of X, I can take minus the log of P of X as my loss that I will optimize. And then I can use the chain rule to get gradients on my model's parameters within my conditionals and train by regular gradient descent. So they're fairly easy, at least conceptually, quite easy to train. And they're also easy to sample from, though they might be slower than directed graphical models with latent layers, in the sense that all I need to do, again, is ancestral sampling, but here I'm sampling one dimension at a time in the order that I've chosen. Yes?
Is that just a visual variable, or is it all?
No, it's just a visible variable. So here it would be all the pixels in my image. And often I'll just assume that images are binary, which is, of course, often not the case. It might be true for, like, if you're doing segmentation and you want to generate a mask over an image. So that could, you can think of that as a potential application for binary images. But yeah, X is really only the observation dimensions. And now, one of the cons of that approach is that you, as I said, don't have an explicit natural latent representation. So if you want to use this for not generating data necessarily, or trying to search over likely observations X when you're doing, say, denoising, but if you actually want to learn a latent representation that you use in the context of semi-supervised learning, it's not necessarily as obvious how to exploit autoregressive models. So I'll show an example of that. So it's that is true. But in this case, we're going to rely on the fact that none of the X's are latent. They're all observed. And because there's no explicit variable that corresponds to a latent representation of my input X, it means it's not clear what latent representation do you extract from a model like this. But I'll give an example. I mean, it is doable. It's just not as natural. Other questions? Okay. So let me just give a little history of at least as far as I understand it, for generative models, autoregressive ones specifically. So autoregressive models, they're definitely well known in the literature of modeling sequences because it's very natural. Then there is a natural ordering, which is usually time. So they're used a lot for time series, for language modeling. They're effectively autoregressive models. But they're less obviously applicable for non-sequential data, which I think is kind of the neat thing about these models here, is the observation that turns out often we can kind of use a random ordering of the dimensions, as we'll see. Or for images, there are certain orderings that even though you would think there's no way this image was ever generated this way, turns out if you make that assumption, the neural net schemes can correct for those and still get a very good generative models. So it's kind of the key interesting thing about these types of models applied here, is this extension to non-sequential data. So yeah, as far as I understand it, one of the first autoregressive model on arbitrary, high-dimensional X observations I saw it from a paper by Brendan Fry, and I think Jeff is on that paper as well. And I think it was a paper on evaluating Helmholtz machine, and it was used as a baseline. So I don't think it was even proposed as an actual model. It was just a thing you could do where you would use logistic regression models, so log linear models for all the conditionals, and then you can get an actual likelihood, and you know that's a likelihood you can trust. It's a real distribution that sums to 1, and it was surprisingly good. And then not so long after, Yashua Benjo and Sami Benjo produced a paper where instead of using log linear models, they used neural nets for these conditionals. There's a sense in which all the neural nets for the conditionals were different neural nets, though there was some form of parameter sharing. And one of the things that they noticed is that they had some problems with overfitting by doing that, though they addressed it in some regularization, with some regularization scheme that was essentially pruning some weights. And then when I did my postdoc, we sort of designed our first autoregressive model with Ian Murray, where we essentially used a different parameterization of the conditionals, a different type of weight sharing between the neural nets. And it turns out I learned later that Carol Greger and Jan Lequin, Carol now being at DeepMind, had come up with more or less the same model at the same time, though he never published it. It was just on archive. But I feel it's only fair to mention it here. And then later on, there was a series of models, some of which come from me and my collaborators, but also some from DeepMind, like the Pixel CNN that I'll get to cover a little bit later on. Okay. Any questions at this point on the sort of background? Yeah? All right. So let's look at our first autoregressive models, which is the first one that me and Ian published. So we called it the Neural Autoregressive Distribution Estimator, or NADE for short. And the idea is fairly simple. I sort of already hinted at it. For all of the conditionals, I'm going to use a neural network, but it's for now with a single hidden layer. And in fact, conceptually, I'm going to use just one neural network. So not different neural networks for the different conditionals. It's going to be the same neural net using the same hidden weight connections for all of the conditionals. So the way it works is that to get my distribution for dimension k, and we're going to assume binary observations. So in this case, all I need is what's the probability for that dimension to be equal to 1. So that's why my output is going to be a sigmoid. I need a number between 0 and 1, and so the probability of being 0 would just be 1 minus that. And as a shorthand for that probability, I just use x hat. Because you can kind of think of it as a reconstruction of the real, kth dimension in the input. So the way I'm going to compute that is I'll first compute a hidden layer. And my hidden layer will just be a linear transformation followed by nonlinearity like we're used to with neural networks. But the key here is that this matrix W of parameters is the same no matter which conditional I'm computing in my ordering. Specifically in this notation, so x smaller than k, that corresponds to the subvector of all the dimensions from 1 to k minus 1. And so this index here for my matrix W is just taking the first k minus 1 columns of that matrix W, plus a bias. But it's always the same matrix W, it's always the same B, no matter what the value of k is, no matter which conditional I'm actually modeling, I'm making a prediction for. Another way you could represent that, by the way, is you could ignore this, the selection of the columns of W, take the full matrix, and I could take my full x vector, but then sort of mask the dimensions from k onward by applying a multiplicative weights like you do with dropout. It would just be a dropout mask, which would be 1 for all the dimensions up to k minus 1, and then 0 from k to the last dimension. That's another way. So you could take that full vector. So all the zeroed out dimensions, they're effectively not involved in the computation here. That's another way of thinking of it. And then I take my hidden layer. I'm going to multiply it by some output weights. So here it's a vector. I'm going to collect all the output weights for all the conditionals in the matrix V. So Vk, that's just the kth row of matrix V. So for different conditionals, I will use different output weights because they're different dimensions, so they have different distributions. And then I'm going to have a bias that's specific also to that dimension. Yes? Yes, Jeff?
Try making B be proportional to K. So just change that equation and put a K in front of the B.
To have B proportional to K. Is that you?
When you've got lots of input to it in units, you can have a bigger balance.
We have not tried that. I'm trying to wrap my head around when you have a lot of input in, because B is for the hidden units and X is for the input space. And why are you suggesting they should be?
Looking at lots of pixels,
Mm-hmm.
it's getting lots of weights contributing to it.
Yeah.
But it's only looking at one pixel. It doesn't have much contributing to it, so it should have a small bias.
Right. So that would be essentially B proportional to, the number of which conditional. So making B sort of variable somehow. I think I think we looked at, I looked at a version of that where I have a vague memory, this is like 5 years ago. I have a vague memory of maybe trying something like this and it not really improving. I will address, there's another thing you can do though, which effectively makes the bias dependent on how many observed dimensions, which I'll talk about in the next slide actually. So, and in that case, it will actually be useful. So I'll come back to that question. Yeah. Yes. Rich.
So there's dependence amongst the different conditionals because they share all the same up to the dimension.
Yeah.
I'm just wondering whether that's so that can be a good thing or a bad thing. Right? So have you looked at?
Yeah. We will see the other model made, which doesn't have that property or not in this way. And effectively what we found is it does seem to help. That is, it regularizes in a good way. Part of the reason I think, so here I'm just giving you, the simplest description of what this model could be, which is just as neural nets used for the conditionals. My original inspiration was then from the RBM. So if you know the restricted Boltzmann machines, that means you're probably at least 30 or more because people don't use those anymore. But if you look at approximate inference in RBMs, they kind of look like these equations. And the idea here was to use essentially one iteration of mean field in an RBM as our model for these conditionals. And it turns out they're essentially neural networks. And the RBM, like part of the reason we were inspired from it is that, in particular on binary images, it was doing really, really well. Some of the results by Russ and Ian on trying to evaluate the partition function suggested really, really good, log prob estimates on test sets. So, yeah. Other questions? Yeah. So, just to sum up, the way we would compute all of our conditionals then would correspond to following this essentially computation flow graph. I would take my input x, and I would compute the hidden layer for each dimension. So the hidden layer h1 for the first dimension actually depends on nothing because it's the prior of the first dimension. This one will depend on the first dimension. You can see there's only one upcoming arrow. This arrow, sort of think of it as the weight vector connecting the first dimension with the second hidden layer here. For the third hidden layer, I'm actually going to reuse the same weights that connects with the first dimension. That's what I'm trying to illustrate with these blue dots here, saying that these weights are tied, essentially. But also, because it's the third hidden layer modeling the third conditional, it also gets to see the second dimension. So you can see this these incoming weights here. And once I have all of my hidden layers, I can each multiply them by their corresponding weight vector, v, v1, v2, v3, and so on. And then I get at the output, after the sigmoid, I get the probability, according to my model, that each dimension is equal to 1. And then I can compare that probability to the actual observation. So did I assign a high probability close to 1 when the input dimension was 1, or did I mess up and do the opposite? And so I can compute a loss, which would be the log probability of the actual observation, according to my model. And then I can maximize this by gradient descent. Because all of these operations, their matrix multiplies in nonlinearity, so you can actually backprop through them, no problem, and actually learn B, W, V, and C. And also, if you wanted to sample from the model, you would do as follows. You would compute the first hidden layer H1, multiplying by its output weights. So that gives me a probability for I am losing my mouse. Okay, for the first dimension. And then that probability, it's a number between 0 and 1, I can sample a one with that probability, and that will be my sample for the first dimension. Then I essentially paste that value to the first dimension in the input, the x. So we'll stick here whatever I sampled up, and then I would compute the second hidden layer, compute the second dimension, gives me a probability, a sample from it, and I stick it here, and I continue like this, sampling each dimension one after another. So that corresponds to ancestral sampling of each of the conditionals in sequence. And that will give me a sample from this model. Okay? And now you might think that doing that process might be expensive because I have a lot of hidden layers to compute, and each are connected on average to half of the inputs on average. So, as you go towards all the conditionals, you have more and more inputs to connect to. And so this multiplication here becomes more and more expensive, the top one. But because between adjacent hidden layers, the linear term inside the sigmoid, the only difference, if I subtract them, is the contribution from the new dimension. So the contribution is just whatever next dimension I'm observing times the corresponding column vector in W. So what I can do is that to compute the next pre-activation before the sigmoid, I take whatever I computed previously and just add this vector. So it's going to be linear in the number of hidden units to compute the next hidden layer. And I have number of dimensions, input dimensions, let's call that D. So it means it's still linear in the input dimension and number of hidden units. So it scales with the same complexity as regular neural networks, thanks to this trick here. Okay? Any question on this model? Yes? Mm-hmm. Why is it a natural model? It is definitely not a natural model. I would not describe it as a natural model for observations in general. We worked from certain computational properties that we wanted, and then sort of backtrack from this into a model that had enough capacity. And so I would definitely argue that here, this is a purely data-driven approach. We're going to have a lot of data, hopefully. We're going to have a model with enough capacity, and it's going to have the computational properties we want, which is we can compute P of X, because maybe that's, that assumes that's something we want. And also, it's not going to be complicated to train in the sense that it's backprop in a slightly more complicated computational graph, but it's still just backprop. There's no variational inference. There's no generator and discriminator. It's just backprop on the LOC problem. That's, the appealing thing to this. It's not that, of course, images are generated this way. At the same time, I would argue that a lot of generative models are not necessarily that natural either. Like, if you assume that images are from a latent representation down and that generates all the pixels, that's still like making a lot of other assumptions that are probably inaccurate. So, we can argue on which model is more, makes fewer bad assumptions, but they all kind of make, unreasonable assumptions to some extent. Yes? Yeah, so groups, it would make sense. Yeah, we just did the simplest thing, which is treat each dimension as a separate one. But that could be something where you could sort of model more complicated, correlations and dependencies between, say, adjacent pixels in an image. So you could imagine putting blocks of pixels, like 4x4 blocks in sequence. That's totally doable here. You're essentially just changing what X is. Yeah, but you could definitely do that. That would probably help model more of these sort of local correlations between, small neighborhoods, which if it doesn't nail this, if you observe your data is struggling at that, then doing something like this would make sense. All right. Oh, yes.
Recently, there's some work on unrolling the in-field inference of CRF as a recurrent neural net to train the CRF on top of CNN drawing.
Yeah.
Steps in there, it sort of looks like a autoregressive.
Yeah, so the idea of unrolling the inference steps of a graphical model as a model, there's this work, but there's before that, like at least 5 papers probably on more or less exactly this idea. And this is an exploitation of this idea here again, but for, modeling data in general, not necessarily just images, I mean, this idea has been in one shape or another found in multitudes of paper, for sure.
Do you think autoregressive autoregressive model in general can be used as some sort of inference of energy-based model that we just don't know about?
I mean, I'm sure you could sort of torture the math until you see an energy function pop up, but I don't know how natural it would be. I mean, maybe there's, maybe there is, but I don't know. Any other question? Those are all good questions, so don't hesitate. All right, so that was the single hidden layer version. Now, how can we make it deep? Because deep neural nets are usually better. Well, normally, what that would correspond to in terms of the computation graph is that I would just make these layers like this and add another one on top. Now, however, if you do this, then let me just, sorry, because I lost my mouse somehow and I can't draw anymore. All right, screw it. I'll stop drawing then. So now the problem here is that computationally, it's much more expensive now, meaning that now for each dimension, I am going to have to do this matrix vector multiplication, assuming that there are h hidden units in both layers, then at h squared times d, the number of dimensions. And so now actually predicting all the dimensions in sequence is going to be too expensive to actually get a gradient step. So, the credit goes to Benny, who's Ian Murray's student, who came up with this idea. They made the following observation. So at the same time as we're going to try to use deep neural nets for this innate model, we're also going to solve the other uncomfortable thing about these models, which is that you have to come up with an ordering. None of them are actually really satisfying. And even more comfortable is that a random ordering, which is convenient, but a random ordering actually tends to work surprisingly well. But the fact is that we might want a model that is somewhat agnostic to what ordering you put the dimensions in. If anything, so you can do any type of conditional inference. So if you wanted to do, okay, what's the distribution over the first dimension given all the other ones? Well, that's a very awkward conditional to compute. Well, actually, not that much because the normalizer is just over one dimension. But let's just say the first half of the vector x given the last one, that's something that you can't really compute exactly. But there would be other orderings where if you had trained your model in the inverse direction, you could actually answer that question. So the idea here is that we're going to have a model. It's going to be deep, and also it's going to work on any ordering. That is, it's going to be possible, we're going to train a model to be able to give us all the conditionals in, say, this ordering here, 1, 2, 3, and 4. And also, let's say, 1, 2, 4, and 3. So we want a model that we can use for any of those orderings. And the key observation here is that if we consider just the conditional over the third dimension, given the first two, well, if I've computed all of that, I know that there's another ordering where I would like to compute the distribution of the fourth dimension given the first and second dimension. And I've done most of the work here if I've computed the distribution over the third dimension. All I need to do is reuse the top hidden layer and now instead multiply by the weights for the fourth dimension. So now this suggests a different way of training the model where instead of choosing an ordering and predicting in sequence all the dimensions, I'm going to instead randomly choose which dimensions I'm going to condition on and predict all the other ones. And effectively, what I'm doing now is training a single neural net to give me each of the conditionals for each of the output dimensions, given the conditioning input. And the way we do this in this stochastic way, where we take the inputs, we shuffle them randomly, we randomly pick a splitting point, and whatever is left is going to be conditioned on, so fed as input, and whatever is right to the splitting point is going to be reconstructed at the output. And we don't reconstruct the other dimensions. So it's somewhat similar to denoising autoencoders, if you know about those. But the big difference here is the way we add the noise, the way we mask certain inputs. So whenever we're not conditioning on x3 and x4, we're effectively multiplying these dimensions by 0. You can think of it this way. So, but the difference here is how we generate this masking noise. And also at the output, we don't reconstruct all dimensions, which is what you do for denoising autoencoders. Here, you just reconstruct the dimensions you didn't feed as input. It is, well, there's no notion of reconstruction with dropout, right? But masking is, similar to dropout. And the other thing we're going to do, which kind of addresses the issue that Jeff mentioned, is that for the dimensions that are, actually this is wrong. For the dimensions that aren't missing, we're also going to essentially concatenate a vector corresponding to the multiplicative mask that we apply to the input. That is, this binary vector is indicating to the first hidden layer what are the dimensions that are really there, and what are the dimensions that were essentially multiplied by 0. And so this allows for the bias to be a function of how many inputs are present, because there's going to be weights multiplying this binary mask, and the more essentially the more inputs are present, it could determine either to decrease the bias or increase the bias. It can essentially learn that in the connections between the binary mask values here into the hidden layer. And what we found is that, so not only does it allow you to have biases that depend on the number of observed inputs, but also which inputs are observed. So it can depend on which one are actually there and how should that impact my effective bias for my first hidden layer. So the training procedure is now very similar to an autoencoder. We just add some noise in the input. We add by masking with a binary mask. And we feed that mask as input to the first hidden layer. And at the reconstruction, we only reconstruct the dimensions that were not fed as input. But it's a forward pass and a backward pass and an update, and we move on to the next example, regenerating the binary mask. Okay? Any questions about this? So some of the properties of this model is that if I fix an ordering, now I do have to compute all the conditionals if I want the distribution over the full vector x. So that means that I'm not escaping, if I want to compute P of x for a given ordering, I'm not escaping the complexity that's squared in the number of hidden units and then linear in the input dimension. So that's going to be inefficient, but that's only at test time. And it's still somewhat reasonable in certain cases. I saw a hand, yeah.
So you're saying that each backward pass is a different random order?
Yes, because we want to train on essentially all orderings. So we want the average log likelihood over all orderings to be good in this model. Implicitly, that's what we're doing. And I'm adding some math that sort of implies a particular scaling of the, that complexity is in the paper, but effectively, that's what we're doing.
So it's a bit like dropout as you put.
It is, yes.
Except that you're shifting it. By requiring orders, you're shifting it. The number seems to be 0.
So so there's sort of a not trivial probability for a dimension to be 0, 1. The process is more complicated in that we shuffle and then we uniformly pick a splitting point. So there's a bias towards, like, I guess a number of, I don't know what the marginal distribution looks like for the number of zeros versus ones, but it's not necessarily the same as the one you get with dropout with some probability. It's structured. Yeah. So we can compute. Oh, yeah, sorry, James.
Question about clarity, but this models not only the individual distributions in the ordering that you talked about originally, but also blocks of conditionally. You can sample as many as you like, right?
Yes.
Sampling algorithms for an entire set of variables.
Yes, which is the ordering. So I give an observation.
Distribution, if you sampled each one in order, versus if you did like more of a Gibbs sampling type thing.
So let me try to. I'm going to make a statement about this. Let me know if that corresponds to what you're saying. So I'm not sure I can. So here I'm essentially assuming a uniform distribution over orderings, and I'm not learning it. And I'm also not doing what some people would, if you're sort of more familiar with graphical models where there's a latent variable, I'm not doing any inference over what is the ordering for that input. I'm just sampling all orderings and assuming they're always equally appropriate for any given input and training that neural net on whatever ordering I sampled. And I did that uniformly.
Totally valid.
Okay, but that's, yeah.
It doesn't force you to make all those choices. You're free to choose whatever sampling strategy you like, which might not.
I see. So I guess you're asking whether you're free to choose whatever sampling scheme for the ordering. So the way we derive that is from the fact that we wanted the average log prob over all orderings. We wanted to minimize that. If we want to minimize a different weighted average over orderings, that would inform a different way of generating the masks. Does that make sense? So now there is one thing which you might have noticed, which is that for two given orderings, the conditionals are not necessarily consistent with one another. I'm not applying Bayes' rule to get one conditional given another. I'm just learning an inference network effectively, which means that for different orderings, P of X is going to be different. And now that sounds like a bug, but you can turn that into a feature by saying, well, that means I can construct an ensemble for free by just saying, okay, I'm going to construct on the fly 128 models from the same neural net using different orderings of my input dimensions. And for each, I'm going to get a LOC prob. And then I can just average these probabilities. And that still sums to 1. And it turns out that the more orderings you add into this estimate of what is essentially marginalizing over the latent variable, which is the ordering, gives you better and better LOC prob. Yet the LOC probs all sum to 1. Because each given an ordering, and since we weight each ordering by 1 over the total number of orderings we sampled, each model itself in the ensemble is properly normalized, which means the ensemble is also properly normalized. So essentially, what we found is that with this model, if you want better log prob estimates, you just crank up at test time how many ensembles you sample, the size of the ensemble, and you're going to get better log prob estimates on the test set. Yet the model still sums to 1, so it's not like cheating by assigning probabilities that sum over 1. And what you get here, as I said, is that you essentially have an inference network. So given any subset of the input dimensions, I can just feed that as input to the neural net. And then if I want the probability of the rest of the image, well, what I could do is just pick one ordering of the remaining dimensions and sample those in sequence, always for each dimension requerying my neural net, my naive model. Yes? Yes, Jeff?
Did you ever think about adding an extra term to the objective function where you train it to be consistent? You take two random orderings and say, I can get an extra derivative to make those more consistent.
No, we've never tried that. It seems here, to some extent, we seem to be benefiting from. I mean, if they were consistent, then the ensembling wouldn't help.
They might be better.
Individually, it might be better. I see what you're saying. That's an interesting thought. No, we have never tried that. No, that's interesting. All right. So, so in terms of log probs, when we looked at the binarized MNIST data set, which for a long time was a pretty useful benchmark for measuring the value of these different models. And when we're ensembling, so one thing we consistently see is that if these are the ensemble models, and if we're using, say, just an ensemble 2 orderings versus many more, we'll always get an improvement. When we don't use the input masks, when training and computing the probabilities, we get pretty bad results. So actually conditioning on the input mask is very valuable. And it did very well compared to other models at the time. Those results are not entirely up to date. But, and so those are essentially here, those are the two curves for a single hidden layer and a 2 hidden layer order agnostic naive model. And this is the number of orderings that are sampled, and you can see it's sort of eventually there's diminishing return as you add more and more ensemble, but you get a pretty significant improvement in terms of log probs. And as I said here, you can do conditional inference fairly easily. So unfortunately, you don't see super well, but there's a red square that's hidden that we're going to try to infer given the rest of the image. And there's this one which I like where we've hidden this part of the 5. And so most of the times it generates a 5, but sometimes it generates a 6 because it kind of looks like a proper 6. So that's kind of interesting. So it seems to have learned, interesting conditionals also for different types of conditioning problems. So you might not see here, but the red square is sort of positioned at different areas of the image. So you can do arbitrary conditioning, essentially. All right. The next model I'm going to talk about is also an regressive. Oh, sorry. Yes. So no. So we haven't trained it with regular dropout and then see do we get good log problems. I guess it could. I wouldn't be able to explain it though, but I guess it could. Here, the reasoning behind this dropout was really we took the loss we wanted to optimize, and that implied this form of dropout. So, all right. So the other model that I said I would talk about is a different approach to turning essentially an autoencoder into an autoregressive model. Oh no, sorry. Actually, first. I'm going to talk about how do you extend these models to other types of observations. I've essentially assumed binary observations, but it's actually pretty easy to extend it to any other type of observation. So if you have real value data, well, instead of outputting just a single number, which is the probability of that dimension to be 1, you could output the means, variances, and mixing weights of a small mixture of, say, 10 components. And you do that for each dimension, so that increases the number of output weights. But you can evaluate, by essentially marginalizing over the mixture components. You can evaluate the log prob of that dimension, and you can backprop through it. That essentially corresponds to a mixture density network. But now we have one at every dimension. I'll skip over the results since I don't have a ton of time. If you had instead multinomial observation, so if you had, say, a sequence of words which belong in a finite vocabulary, then one thing you could output is a softmax over all the possible choices. So if you have 10,000 elements in your vocabulary, you have a softmax of dimension 10,000. That can be pretty large. They can be expensive. So instead, you could use something else like a tree-structured softmax, which I won't go into. But if you're familiar with the literature on natural language modeling with neural nets, those are the types of models for the output distribution of a language model that you can use. That essentially turns things, instead of being linear in the vocabulary size, it turns it into a logarithmic. And now I'll just skip over that due to interest of time. And I'll go to the other model I want to talk about that's different, but that applies the same concept of trying to, well, let's torture an autoencoder to turn it into a density model. So you have on the left an autoencoder. Now, if you train an autoencoder in the regular way, you know that you can't use the output as actual proper conditionals. It's not training a generative model. Now, why is it that I can't use my outputs as the conditional distribution of that dimension given some other stuff? Well, the reason is that, for instance, if I look at the second output, and let's say I was interested in doing inference from the first dimension to the last, well, first of all, the second output is connected with the first real input. So it has access to more information that I would want to condition on. And not only that, actually this second output actually knows, has access to the information of what the second input is also. So effectively, actually, an autoencoder with enough capacity can easily just copy the input as the output. And so it would always answer the right thing because it's cheating. It's conditioning effectively on all the information. But we could avoid that if we did some, well-designed masking of the connections to make sure, for instance, that the second output only has a pathway towards the first dimension and not the second and not the third. Okay, so how could you do that? Well, we designed a procedure, and we called that the masked autoencoder distribution estimator, or MADE. And here's a simple procedure for doing this. It's not necessarily the only one, but this one's very simple. So I'm going to describe, in fact, a procedure that works for any ordering. So the first thing you do is you determine what ordering would I like. In this case, I'm going to assume that I want to model P of my vector x as P of x2 times P of x3 given x2 times P of x1 given x2 and x3. Okay, so that's what the number shows here. It's the first, second, and then third dimension. And I'm going to have this number associated with the output units as well. And then for each of my hidden units, I'm going to arbitrarily assign them a number of how many inputs in that order it is allowed to be connected to. Okay? So here I've sort of randomly chosen that this hidden unit gets to see the first two dimensions. This one, just the first dimension. This one, too. This one, too. In our case, so you essentially sample, and we use uniform sample, a number from 1 to the number of dimensions minus 1. So there's no point in sampling 3 here because that would be a hidden unit that cannot be connected. That would be connected with all the input dimensions, but then I can't use it for any of the outputs. And given this number, then it's very easy to just infer what the mask should be. So essentially, for instance, if the number of this unit is greater or equal than the number of the units here, then I don't mask it. I only mask it if the number here is greater than the number here. Because this is saying it can only be connected to the first input, so it can only be connected to hidden units that are connected with the first input. And that's only this one. Whereas here, well, 2, you're going to be connected with everything here. And this one is only connected to that. And so it's easy to just construct a binary mask where you make this test for every pair. And then that gives you a binary mask. And then you can apply this binary mask on the matrix W. And so it's a type of dropout that's closer to like drop connect, which was this variant where you were multiplying the connections instead of multiplying the units. But here again, it's structured. And it's structured in a way to enforce what I call the autoregressive property that ensures that I can use the outputs as conditionals. And then in this model, if I use the reconstruction error like for binary observations, the binary cross-entropy, I'm effectively maximizing the log likelihood under this autoregressive model. Okay? And it turns out that this is essentially a more general form of the original paper by Joshua and Sami Benjo, where you had different neural nets for each of the conditionals, but they allowed for some form of weight sharing. Essentially, a conditional for, say, the kth dimension had access to the hidden units of the previous neural networks. This is effectively what it's doing, but it's doing sort of in a random way. And it also generalizes the procedure to deep neural nets. And another thing you can do here is actually use several masks. So you can, so normally if you want to train on just one ordering, you sample the masks once and for all, and you keep those around, and you never change them. You always train with that mask. That means a lot of the connections are never trained, but they're also never used, so that's fine. But you could imagine actually resampling these masks several times, and that would correspond to training on all possible orderings. What we found is that because you see that there's a lot of hidden units that are connected to barely anything, they're almost wasted to some extent. Like some units are essentially used for very few conditionals. So the full capacity of the network is to some extent not used. What we found is that these models need to be much larger for a model like MADE compared to NADE to reach good performance, at least on binarized MNIS. Yes? Yeah. In the sense that, for instance, I could say, well, actually, this one, I don't want it to be connected to this one. That's true. We try to enable as many connections as we can, given these constraints, because that's just more weights that are being used. But you're right. I mean, you could imagine other ways of sampling masks that still satisfy the autoregressive property and that aren't this procedure. Okay. So I should say that it's the same complexity as regular autoencoders. Forward pass, backward pass. You just apply these masks. Now, unlike NADE, where the mask is essentially on the input, here the mask is on the weights. However, you reconstruct the full output. And unlike NADE, Sampling is kind of annoying. You have to do, again, a forward pass for every dimension, kind of like Nate, so we haven't solved that. And as I said, in practice, we found that you need a pretty big model to be competitive with NAID. Okay. So those are sort of these two different approaches for autoregressive models. And what I'll try to do in the last minutes that I have is to go over some of the, is that right or am I wrong again? No, yeah. Go over some of the more recent work on specifically tailoring any of these two approaches to images. So I have talked about, applying these two images where we just use random sequence of pixels, but there is structure in images. There's a notion of a topology of pixels where we expect stronger correlation between neighboring pixels than pixels are far apart. So, much like, there's been a whole lot of work on doing that with neural nets, yielding convolutional neural nets for classifying images, we can apply some of these ideas here for generative models. More or less, the solution is going to be, indeed, apply convolution layers instead of fully connected ones. So if we want to do this for NAID, instead of having the fully connected set of layers, or in addition of, you can actually have two, the fully connected pathway, and then you can also have a convolutional pathway. Because all we're doing, really, to satisfy the autoregressive property is just adding the binary mask and masking the input. So we can just apply, this mask, convert it back into an image, and then apply convolutions on those. Okay? And that, indeed, in terms of the log problems we can get, this was applied on binarized MNIST. Instead of getting something like 85-ish, we get something like 80, which is around, even today, the state of the art. So that's for NAID. And the benefit of this approach over the next model I'm going to talk about is that you can do inference for any, if you can mask any part of the input and do inference of the remove path, part of the input. If I wanted to do that with MAID, and in fact, interestingly, we wanted to do it. We had the idea, but then DeepMind came up with their Pixel CNN paper, which is effectively trying to take a model like MAID and that approach of masking the weights to convolutional neural nets, and they call that Pixel CNN. Well, so what we would like is have an autoencoder-like model where at the output, what you get at a given spatial position, so your output layer is convolutional, so it is a feature map. And then at a given spatial position, you have the distribution over what that pixel at that spatial position should be. Okay. So much like MAID would give you a distribution at every dimension of a vector x, here, because these are images, I have an output layer that's convolutional, and at every spatial position, I have a distribution over pixels. And it can be, and in fact, they've applied it to RGB values even. So you would get then a distribution over the red, green, and blue channel. And the way you do this, it turns out, is with masking. So instead of masking the weight matrix, you mask the convolutional filters. And the way you mask them is you make sure that everything below the center value of the pixel, and on that same row, everything right of that position, including the center pixel, is masked, is set to 0. So the center pixel kind of makes sense, because if it wasn't masked, then the same pixel could influence its own distribution at the same spatial position, because the central pixel is essentially corresponds to information at that position. And we're just assuming here, we're going to assume a dependency that's essentially from the top left and then left to right and then top down in terms of the autoregressive ordering that we're assuming here. So if we use that kind of masking at every layer of a deep convolutional net, we will satisfy the autoregressive property. It is such, and I mean, I'm not going to try to explain why, but it is such, however, that there's kind of a blind spot. If you have several layers with this masking, there's sort of this spot on the right, sort of in the corner of the upper part, that is actually not influencing the distribution predicted at the output at the center. Because sort of removing that part on the right sort of accumulates to some extent. So fun exercise to think about why that is. And also, if you're doing RGB, you're going to want to be autoregressive with respect to R and G and B. So you're going to effectively generate R, and then R you're going to generate G, and G you're going to from R and G generate B. You do this by having different feature maps for R, G, and B. And at the first hidden layer, you're going to make sure that the center pixel red doesn't influence the center pixel of the feature map red. But then for future layers, you can have this vertical relationship. However, red will influence the green feature maps and the blue feature maps. That's fine, because here we're assuming from red to green to blue. One interesting thing that they did in this paper is that they, first of all, I mean, correctly in terms of how the image is encoded, assume that the pixel values are discrete from 0 to 255, which is correct. However, instead of modeling the fact that 255 is closer to 254 than 0, they just assume those are like word IDs. 0 is as different as 255 a priori, and then hope that the network is actually going to learn that. So it's kind of like having a very powerful but somewhat awkward mixture model where you have a single probability for each component, and it isn't aware of the ordering between the pixel values. And what you can see on the right is the learned distributions for a few different cases. And you can see that the distribution is somewhat smooth. It's not perfectly smooth, but it's somewhat smooth. Recently, the folks at OpenAI tried to improve over this model, and they proposed a way of incorporating that assumption that similar color values should have similar probabilities. It actually turns out that does speed up training. The model is called Pixel CNN++. If you want to look it up, it's an iClear submission. And there are other ways you can improve this. So this was first proposed at ICML in 2016, and then at NIPS 2016, they figured out a way of removing that blind spot, which seemed to have improved performance further, making it the current sort of, in terms of tractable models for images, the state of the art. And the way they do this is they have different types of convolutions that are masked, but one essentially just models what is over the current row, and another one models what is left of it. So you have two different filters being convolved, and you have sort of, I don't know if I have a picture, but you have a more sophisticated kind of gating mechanism within each layer that makes sure that you don't break the autoregressive property while making sure that at any given layer, you always get to see everything that's over and everything that's to the left. I'm not going to try to explain it here because I will probably fail, but the details are in the paper. It's just not that intuitive beyond what I just said. And yeah, those are just the results this is on CFAR 10, showing some pictures. So these are the images sampled by Pixel CNN model in this recent NIPS paper, but it's actually a conditional model. So here was conditioned to generate coral reefs, horses, sandbar. And you can see those are, at least, if you don't pay too, the sort of problems with the projector are helping here. If you don't look too closely, it is convincingly from any one of these classes. Like a lot of these do look like they have a horse in the image. Those are small images, but there's also like improvements to make them fairly high resolution images, like 64, and maybe 128 by 128, I think. And what is nice about that is that these models actually guarantee to like they don't assign zero probability to real images in the test set, which is something that's hard to test for what seem to be better generative models like GAN models. So here you don't have this concern that you might have, which, if you care about probabilities, if you're compressing images, that can be a useful quantity to have. This might be more appropriate. And I just quickly mentioned that recently, so this block of pixel CNN is something you can stick in more complex models. So for instance, you could model each of the frames in a video, conditioning on previous frames, using pixel CNN models by essentially adding a conditioning path from using some sort of RNN that could condition on, first and second frame, and in order to influence the generation of the third frame, for instance. And so then they sort of become like Lego blocks. You can more or less plug and play. And I'll just show some images, hopefully. So those were trained on images of So this is a video of a robotic arm that is sort of moving around in a box where there are a bunch of items. Here, this is conditioning on the first few frames that has objects that it has seen at training time, but it's different images. And it seems to have captured things like, if the arm goes close to an object, then the object should move. And they also applied it to images where you condition on the first few frames that has objects that were not observed at training time. And it seems to somewhat generalize to these new objects, though not as well. And you could see that something like this could be useful for planning. For instance, if a robotic arm wanted to see, okay, well, how should I move my arm and how will it affect the world if I move my arm in a certain way, then a model like this would be valuable, because then you can it's kind of like you planning, sort of trying to figure out what will happen if I do this or that, and being able to pick between the better options. All right. So that's it for autoregressive models. I would say in terms of future work that I think is interesting, so I skipped over some of the work that I've done on trying to use autoregressive models to train on a lot of unlabeled data to improve the classification performance, say, for a data set that has fewer labeled examples. I think there's still a lot of progress to be made in that direction. But there's an extent to which doing that, effectively would be very valuable, because there's, of course, usually a lot of unlabeled data. And I wouldn't say that, we know we should be able to do this. I don't think we're happy with how good we are doing this. And this, provides a path towards this. I should address at least the mention that I said, that there isn't a natural representation. So the way you could do it is that if you have the name model, you could assume that my ordering is any of the first dimensions x, and then finally the label y. So assume that in my ordering, the last dimension is always the label. So what that means is that whenever I don't see the label, marginalizing out the last dimension is trivial. It just means, just act as if it's not there. But when it is there, you actually try to predict it. So it means that you can still, you can motivate using the hidden layer to also predict the label whenever it's there, or not predict it when it's not there. And that becomes your latent representation. And we've applied this to images where we sort of took the images and transformed them into bags of words, because at the time this was the approach taken for that data set, with some success. Like, we would see that we had 1 million unlabeled images, and the more we trained on these unlabeled images, the better we did. So that is applicable, but I think there's still a lot of work to be done in trying to making that more effective. And some of the applications that I mentioned, such as denoising, or specifically for reinforcement learning, helping with planning, we are definitely not at a point where learning generative models in an environment is good enough to improve reinforcement learning in a meaningful way. I think there's a lot of interesting work to be done there, which I hope to do myself. And I think, is clearly at a point where, given all of the different benchmarks we have for reinforcement learning, where it makes sense to start tackling and investigating that approach, either to help with exploration. So there's some work on using a density model to extend count-based exploration. That's one application here. So I think there's still a lot of stuff to be done here to try to exploit models in this way. And I think I'll stop here. Thank you. Sorry, yeah? Yes?
Do you guys say that generative models are close to being solved problem?
I'm not sure I would say close to be a solved problem. I think we've made important progress, and that's encouraging. But maybe it's my nature to not make bold predictions where this is going to be solved. But it's still a hard problem. I think there are some non-trivial things to be discovered still, in particular in the way we use them effectively for other things than just computing LOC problems.
All right. Well, thanks a lot, Hugo.